thank you very much for having me here. So I chose as title Multimessenger Constraints of Gravity. I actually didn't put gravity in that color, but somehow it's highlighted here through the beamer, so there might be some secret message for you, I don't know. So I will not be talking so much about observational constraints, but rather try to give you an overview how we can look at gravity from different perspectives, okay? From different approaches, and how we can basically understand the theory of general relativity from different perspectives, but also try to modify it in a consistent way. So as you might know, modern cosmology deals with the origin and evolution of the entire universe. And if we want to say something about the entire universe, we need to have a fundamental theory of gravity, because it's the fundamental force on these cosmological scales. So, but thanks to Einstein, we already have a fundamental theory of gravity, namely general relativity. He introduced it already in 1915, and he used this geometrical perspective where he describes gravity due to the curvature of space-time. Okay? So gravity manifests itself as the geometric property of space-time, and he puts the curvature of space-time equal to the existing matter fields. Okay? There's also the equivalence principle and the fact that all the matter fields should feel with the same strength the gravitational force. Okay? And with this, he was then basically able to write down the fundamental theory of general relativity purely from geometrical perspective. So gravity is due to curvature of space-time. Okay, this is fine. Let's visualize that. Imagine we start with simple Minkowski space-time, completely flat, and now we put an object, a mass, in this flat space-time, like Earth, and due to the presence of this matter field, the space-time gets curved, okay? And this is how the gravity will manifest itself. And now if you put a second object here, then this object will feel the gravitational force due to the curvature of space-time. Okay? It's not like there is one force that propagates from that object to that, but in this interpretation is rather because the space-time is curved that these guys know from each other. Okay? So this is this geometrical view of gravity. And in this geometrical description of Einstein, everything is basically in this manifold described by the metric, this G mu metric, this tensor here. And the connection in this manifold is completely given by the Christoffel symbols, which is determined in terms of the metric itself. Okay? And so basically the curvature are then the derivatives of this metric, and everything is dictated by this metric, G mu. This is our gravity. So if you might have forgotten from your general relativity course, here is the expression of the Christoffel symbol in terms of the metric and its derivative. Okay? So general relativity is basically nothing else but a pseudo-Riemannian manifold that completely is determined by the metric G mu. And as I said, the connection is given by the Christoffel symbols. And in this formulation, or in this interpretation, we have a Riemannian, so we have the Riemannian tensor, the Riemann tensor, which is non-zero, because we say gravity is due to the curvature of space-time. But we have torsion equals 0 and non-metricity equals 0. And this guy, non-metricity, is something that you probably usually don't see in your textbooks. This is because in general relativity, this non-metricity, which is the derivative applied on the G mu on the metric, is equal to 0. But in principle, if you have a more general manifold, you could have all of these important objects besides the Riemann tensor. Okay? So if you want to visualize that again, imagine if you have the Riemann tensor, if you have curvature in your spacetime, what does it do? Well, imagine you take a vector, let me take my pointer, and I move it along a closed circle, and I come back to where I started, and if this vector now points to a different direction, it means that my spacetime has a non-vanishing curvature. Okay? So I start here, I go around, and I end up pointing towards a different direction. What about the torsion? Well, if I have torsion in my spacetime, and imagine I have two vectors, maybe let me take also this one. I have two vectors, and I now move this one vector along that guy, and the other one along this, and if at the end they don't close, is because my spacetime has torsion. Okay? And how about this non-metricity? This guy that we usually don't see? Well, this is basically, I cannot illustrate it with the pointer, but imagine the length of the vector would change when I move it along a curve. Okay? So the length of the vectors would change in such a space-time. Okay, so just to summarize, general relativity, Einstein's formulation of gravity, is non-flat, torsion-free, and non-metricity-free geometrical description of gravity. Okay? This is just one geometrical interpretation of gravity that Einstein introduced in 1950. You might wonder, since you already introduced this type of geometrical objects, like this torsion and the non-metricity, could it be a more general geometry if I base my gravitational theory on a more general manifold? And of course, you already see it. Of course, yes, it can be a more general geometry. And in this respect, in the literature, people have considered all different types of manifolds, general spacetimes. So if you have the most general spacetime that you can think, then in this manifold you will have your Riemann tensor, your non-metricity, torsion. Okay, everybody is in there. But you could be also interested in some subclasses. For example, if you assume you still have metrocompatible manifolds where the non-metricity is zero. For example, you can have this Einstein-Cartan spacetimes. As you can already see, Einstein himself got involved in this type of gravity theories, where you have on top of the Riemann the torsion being an important geometrical object in your theory. And you see general relativity, just the standard pseudo-Riemannian geometry sits here, when you also set torsion equals zero. People have also considered this Heisenberg spacetimes, so also known as teleparallel gravity, which is completely based on torsion, where you don't have the curvature in the standard way as we have in general relativity. And actually, you can write general relativity exactly the same theory with the same physics, with the same equations in terms of torsion. Okay? And yeah, of course, the Minkowski spacetime, maybe a bit boring, sits just here, where everybody is just set to zero. Maybe not that boring, but okay, you can do a lot of field theories there. Here is also the non-metricity, the Q geometry that sits here when Q is not zero. And I just want to highlight one recent work that we have done with Jose and Tommy. And so this is what we call here coincident general relativity, and is based on this Q geometry. Okay? So the fundamental object in this description of gravity is the non-metricity. So the guy that is responsible that the length of your vectors change in that space-time.
In your picture, where is the cosmological constant? In the geometrical side or in the source side?
You can choose it as you wish. But the equations of motion from this theory that I am going to present to you are going to be the same as in general relativity. So you can also have a cosmological constant there. So in this, what we call coincident general relativity, as I said, is completely based on this non-metricity object, okay? And it's a flat and torsion-free geometry. So there is no Riemann, no curvature. The Riemann tensor is not present, and the torsion is also not present. And the Lagrangian is quadratic in the non-metricity in this Q alpha mu guy. And so you write down the quadratic Lagrangian in terms of this object with some given coefficients. And now if you tune these coefficients in a very specific way, you can get the same theory of general relativity. But there is a crucial difference in this geometrical formulation, namely that the fundamental connection vanishes there. So because the Christoffel symbols part of the connection and the part coming from non-metricity cancel each other, and so you are blind to any affine space-time structure. And so if you take this quadratic Lagrangian in terms of this non-metricity and choose these coefficients in this way, you recover exactly general relativity, but up to boundary term. So the difference is just due to boundary term. But they are exactly the same theory. It's just a different interpretation of the same physics. Instead of saying that it's due to curvature, you just say it's due to non-metricity. Okay? In the same way as also people were saying that gravity or general relativity is due to torsion. Okay? It's kind of just a different interpretation of the same underlying gravity physics. Okay, this was just to give you a taste of, well, that the geometrical description is not really unambiguous and that you can write exactly the same theory and interpret it in terms of different geometrical objects.
Sorry?
Yes.
The number of degree of freedom in the three formulation is the same, right?
Mm-hmm. The three different theories that I mentioned, based on torsion, curvature, non-metricity, they're exactly the same. They have exactly the same two propagating degrees of freedom. Everything is exactly the same, but the difference is just boundary terms. So anytime when you have a physical scenario where boundary terms might be important in some of the calculations, then you might see the difference. Okay? But as a classical theory, where you don't bother about the boundary terms, they give exactly the same physics. So if you would compute how particles move around, or if you try to get some predictions, they would give exactly the same physics. Okay. But now we are going to make a Gedanken experiment. Imagine a universe in which Einstein did not exist. Okay? So I know this is a really sad thing to imagine, maybe apart from some individuals, but just bear with me. We just imagine Einstein did not exist and did not write his theory in 1915 in terms of curvature. Okay? But instead, imagine we had a modern version of Einstein, like this. And actually, if you Google modern Einstein, this is what you get as the first picture in Google. And I guess Google knows better than me. But imagine this modern version of Einstein would have learned everything, really everything in the development that we had in the standard techniques of field theory description of particle physics. Okay? So this modern Einstein would knew how you write down physical fundamental theories with given spin using the fundamental representations of the Lorentz group. Okay? And this guy then eventually, probably 20 or 30 years later, would have then constructed general relativity purely from field theory perspective. Okay? So I will change now my perspective, and instead of looking at gravity from a geometrical perspective, I would like to look at it as a field theory perspective. And in the same way as we described the electromagnetic interactions, like we say this electron over there knows about this electron over here because they are exchanging a photon, a spin 1 particle, a vector field. Okay? And so in the same way I can say, remember I was saying this object knows about that because of the curvature of space-time. Instead of saying like this, I am now taking the perspective saying this guy knows about that because they are exchanging graviton particles. Okay? And in this field theory perspective, general relativity would correspond to the theory, to the interactions based on a massless spin-2 field.
Is the graviton G mu nu, or the difference between G mu nu and Minkowski?
We are,
H.
yes, we can start with the Minkowski and we ask.
H mu.
Yes, I understood your question. Imagine we start with Minkowski, pure Minkowski, and we say what is the consistent nonlinear interacting spin-2 particle on that Minkowski, then the G mu nu arises out of that, out of Minkowski.
Yeah. Minkowski should be always the background.
Yeah, I mean Minkowski is the fundamental, let's say
the support.
This exactly the fundamental group, the fundamental metric of the Lorentz group, and I can then construct my spin-2 representation. Okay, so then I construct my massless spin-2 representation of the Lorentz group. So this has been, you can basically write it as asking the question, what is the most general Lagrangian that I can write down for a massless spin-2 field, so for a massless tensor, that is Lorentz invariant and has diffeomorphisms and gives rise to second-order equations of motion. Of course, this also satisfies perturbative unitarity and locality, etc. And when you ask this question and you are in 4 dimensions, you already know they are given by the low-lock invariance. It's basically the cosmological constant. Okay, so you have just the cosmological constant in your Lagrangian. Then you can have the Ricci scalar that also satisfies these conditions that I just wrote down. And you can also have a Gauss-Bonnet term. But this guy in 4 dimensions is just topological. So when you compute its equation of motion, then it vanishes. Yes?
Why would you ask for a Lagrangian to be diffeomorphism invariant if you are no longer thinking in geometrical terms? Like what's the motivation behind that? Do you think
yes, if I start with my Minkowski and I have my Lorentz symmetry and I write down the spin-2 representation, the diffeomorphism will pop up, and actually you had it in one of your course. It showed that if you have a massless particle, it has to have this redundancy. Okay. So now you can construct to this low-lock invariance divergenceless tensors. How do you get these divergenceless tensors? You just take the equations of motion of the low-lock invariance. When you take the cosmological constant, you compute the equation of motion, you get the metric itself as one of the important divergenceless tensor. You do the same thing with the Ricci scalar. You compute the equation of motion, you get the Einstein tensor. This big G mu nu is the Einstein tensor. And this is the divergenceless tensor corresponding to this low-lock invariant. So I said in 4 dimensions you don't have this Gauss-Bonnet term, but imagine you were in 5 dimensions and this guy would exist. Then you could also construct a divergenceless tensor corresponding to this guy by computing its equation of motion, or if you write it in terms of the Levi-Civita, antisymmetric Levi-Civita tensors. And so then basically the massless spin-2 field pops up as a unique theory of, basically, sorry, general relativity pops up as the unique theory of a massless spin-2 field, okay? Where you have the standard Einstein-Hilbert plus a cosmological constant. Okay. So now if you have matter fields around, how do they couple to my massless spin-2 field? So this is an important question, not only in general relativity, but also in modified gravity, or even in this different geometrical interpretation of gravity. You always have this question, the freedom of asking, how can I couple my matter fields to the gravity sector? And in general relativity, we usually couple them minimally, okay? So just to the square root of minus g. But in principle, I can couple them to all the possible low-log invariants, or all the divergenceless tensors that I constructed from the low-log invariants. I can also couple them directly to these divergenceless tensors. Okay, it's kind of my choice if I want to couple them minimally or non-minimally. And in 4 dimensions, there is yet another divergenceless tensor that I didn't introduce yet. This is the so-called double dual Riemann tensor. And it's basically given by the Riemann tensor but contracted with these 2 Levi-Civita tensors. Okay? And this guy is divergenceless, and in principle I can also couple my matter fields to this guy. So the reason why you can couple them to divergenceless tensors is because, remember, one of my important constraints was I would like to have second-order equations of motion. This is an important requirement if I don't want to have some instabilities like ghost instabilities. And if I now couple my matter fields to this type of divergenceless tensors, and if I compute their equation of motion and I do partial integration, because they are divergenceless, I make sure that I don't have any third derivatives applying on the g in here, for example. Okay, but I can also, as I said, write them in terms of these Levi-Civita tensors here, all the low-log invariants. They are basically the corresponding contractions of my fundamental objects with the antisymmetric Levi-Civita tensors here. Okay? And basically their property of being divergenceless comes from the way how they comes basically from the antisymmetry of your of the structure of your operators, okay, of these Levi-Civita tensors. Okay, so now this was theory, but now let me go to the observations. So we had a fundamental theory of general relativity and already in 1915, but let me change now the topic a little bit, and let me start with this picture here. You can see here on this picture the Milky Way, our own galaxy. It's basically the projective picture of the entire sky. You probably don't see much, but basically the galaxy goes here around along the horizontal line. I'm not showing you the Milky Way just to talk about Milky Way, but actually to make an important statement that until 1923, so not even 100 years ago, we didn't know whether the universe might be much bigger, larger than our own Milky Way. Okay? So astronomers were observing, you can see that with naked eye, but so astronomers were observing our Milky Way and they didn't know whether the universe could be actually much bigger than our own galaxy. And so the real game changer was then this object. This is the Andromeda galaxy. This is our neighbor galaxy, the nearest galaxy. And so when astronomers in 1923 were observing that, even this object you can see with the naked eye, if the sky is dark enough. And so when astronomers were observing this object, they didn't know whether it was part of the Milky Way or whether it was lying much beyond Milky Way. Okay? And as I said, the real game changer happened in 1923 when astronomers managed to measure the distance to this Andromeda galaxy. Okay? And I could say that this was basically the birth of modern cosmology when we first managed to measure the distance to this object. So astronomers managed to pin down individual stars in our neighbor galaxy, and a very particular class of stars, the so-called Cepheids or Cepheids variable. These are type of stars that pulsate, and they pulsate radially with an absolute perfect periodicity. Okay, so they change their luminosity, and their pulsation period is really almost perfect. And there is a really tight, strong relationship between their brightness and their change of the pulsation period. Okay? And so, using this relation of these pulsating stars, they managed to measure the distance to this object. And they found that this object was lying 2.2 million light years away from us. So to give you perspective, this is like 200 times larger than the diameter of our Milky Way. Our universe must be much bigger than just our own galaxy, Milky Way. And so, as I told you, this was just not even 100 years ago, okay? But even within 8 years after the measurement to the distance of this object, Hubble managed to observe many of these galaxies, okay? And he didn't only observe the distance to these galaxies, but he also observed their velocity. And he plotted this diagram here. This is from his work from 1931. And basically the key message that he had was, he was observing that the further away a galaxy was, the faster it was moving away from us. Okay? So, from just statistical point of view, you would say half of the galaxy they should move towards us, and half of the other galaxy they should move away from us. But what we could observe was that by most of the galaxies, so the majority of galaxies, they were all moving away from us. And not only that, they were moving faster the further away they were. So for instance, this galaxy here, which is like by 100 million light years away from us, had like a velocity of 20,000 kilometers per second. This is not a typo. This is really the real velocity of that galaxy. It's almost like 10% of the speed of light. Okay? So in only 8 years, we then knew that there are many of these galaxies and they are all moving away from us. And this was basically I would say a major discovery that the universe must be expanding. Okay, the expansion of the universe. And you can visualize that as we did yesterday with a few kids in a school. You can take a balloon and imagine these dots represent the galaxies, and because the universe is expanding, here as you can see, the distance between the galaxies gets larger, and this is for all of the galaxies, so there is no center really. Okay? This is what happens with our universe. But now, in modern cosmology, thanks God, we already have really a lot of different observations. And now if we put all these different observations, like CMB, VAO, and also the supernovae, etc., and we put them all together, and we look at the budget of the universe, then we get this very funny picture, if general relativity is the right theory, that 70% of the total budget comes in form of a dark energy, and 30% in form of dark matter, and everything that we know from standard model makes up only the 5% of the total budget. Okay? So we have all these dark fluids here, on the right-hand side of Einstein's field equations in order to be in agreement with the observations, if general relativity is the right theory. So maybe just to span a few sentences about this, let's say, unusual matter and energy form for those who are not familiar. So this 30% dark matter is basically some sort of a fluid that has zero pressure, and so it doesn't want to interact with itself, and it also doesn't interact much with all the other fields, for example with the photon, and that's why we call it dark. And because it's weakly interacting, we call it also cold. So this is the cold dark matter fluid that we need on the right-hand side of Einstein's field equations. And also this dark energy, 70%, corresponds to some sort of a fluid that has negative pressure, okay? And if you are looking for a candidate for this, well, the cosmological constant is basically the simplest candidate for that, because its pressure is minus the energy density, the constant energy density coming from the cosmological constant.
You understand my question before, eh? Whether the lambda is in the left-hand side or in the right-hand side.
Yeah, for me it doesn't make any difference.
There is a difference conceptually. Mathematically you can go from one side to the other, but there is an important difference in the concept.
For me there is no...
because you are talking about the fluid and things like that with the density and pressure and things.
But even if I write it on the left,
geometry.
Even if I write it on the left-hand side, it's gonna not change really the let's say the dynamics of the. I mean, it's still the g mu nu that comes in. There is not something like additional in the gravity sector. For me, it doesn't make much difference, but if for you it does. So for me, it's a fluid. If you put it on the left or right, which has a constant energy density. Okay, and because it has this constant energy density and negative pressure, it can give rise to this expansion of the universe. And this is this lambda CDM model, which is the standard model of cosmology that we use nowadays. In the same way as we have the standard model of particle physics, we can also proudly say that we also have the standard model of cosmology, right? Okay, so far so good, and with this lambda CDM model, we can basically describe most of the observations, or all of the observations. So if you assume general relativity is the right theory, we have dark matter, dark energy. Okay, I didn't talk about the inflaton, but in the early universe, we also need an inflationary scenario and another expanding phase due to maybe an additional scalar field whatsoever. And then together with the standard model, so this is our simple universe with all the ingredients, and if we compare with the observations in the solar system, it's in perfect agreement with general relativity. If we also compare it with gravitational tests that we now also have thanks to the observation of gravitational waves, it also seems to be in perfect agreement with general relativity. And as I said, also all the cosmological tests that we have so far, they also are in perfect agreement with lambda CDM. There might be some discrepancies, but statistically they are not so really relevant. And then you could say, okay, then we know general relativity is the right theory, and we can stop here with your talk. But this is not the end of the story. So I am going to also address some of the challenges that exist still within this simple model. First of all, even if you take general relativity, let's say as a simple theory of a massless spin-2 field, and you compute cosmological and black hole solutions, then you find these cosmological and black hole singularities, and they might indicate that maybe general relativity fails at very high UV scales, at very high energies. Okay? So it's okay, so we can use it as an effective field theory, but we cannot describe the ongoing physics there. We don't have a quantum theory of gravity, so how can we complete the theory beyond the Planck scale? We have the cosmological constant problem. So even if we have the cosmological constant saying that it comes from vacuum energy, and we try to estimate the value using standard techniques of QFT, then we see that it doesn't correspond to what we observe by many, many orders of magnitudes, and this is known as the cosmological constant problem. For many theoretical cosmologists, this was basically one of the main reasons why they started considering modified gravity like massive gravity or higher dimensional scenarios. And as I said, we also need inflation in the early universe, okay? And then all these observational challenges, let's say, even if you assume there is this dark matter fluid that you never, or dark matter particle that you never observed, there seem to be some discrepancies on galactic scales. Some people say that simulation of dark matter particles don't give rise to this Tully-Fisher type of relation or other type of relation that we seem to observe, but we don't see it in the simulations using lambda CDM. Or as I said, there seem to be like some anomalies in the cosmological observations, but they are not so statistically significant, but altogether they might point that maybe the standard model is not really properly working. So for me, let's say the cosmological constant problem and also this dark matter particle that we haven't observed yet, unfortunately, gives a motivation to try to modify gravity. Okay? So this is just another alternative perspective to looking at gravity again and saying that, okay, instead of saying general relativity is valid on all scales, we can maybe assume that on some scales, on very, very large scales or on very, very small scales, it might be modified or it needs to be modified in order to address some of these challenges that I just addressed. Okay, so in the following, I will try to, let's say, summarize some of the important modifications that you can do and see if how you can do modified gravity in a consistent way and if they are helpful, etc. Okay, so if you still follow this field theory perspective and now you want to write a theory, a modified gravity theory that goes beyond general relativity, and you want to keep your Lorentz symmetry, okay, and all the conditions that we said, then you immediately have to face the fact that you have to introduce new degrees of freedom, new additional degrees of freedom. Okay, so when you ask the question, what is the theory behind the massless spin 2 field? This gives you uniquely GR, and any modification that you can then do with it immediately introduces new additional degrees of freedom. Other spin 1, spin 0, other spin 2 fields, okay? So you will always introduce additional new degrees of freedom, yes?
This is irrespective of the fact that you formulate your theory using the Riemann tensor or the torsion or the non-metricity, right? The three of them only have the graviton, so now we are going beyond the three options, right?
Yes, so general relativity basically is the unique theory with the least propagating degrees of freedom, basically. Mm-hmm. If I have, let's say, this non-metricity theory, for example, and I go beyond GR, then I probably have additional vector fields propagating or other fields in there. Doesn't matter if you look at it from a geometrical or from a field theory perspective. You can say maybe this connection are just some fields that I am adding also by hand. So you can also argue in this way. So you can always maybe take as a home message, if I want to modify gravity, I'm going to always introduce new degrees of freedom. unless I am just formulating GR with a different geometrical interpretation without changing the physics. Okay, but if I want to change the physics, then I will definitely introduce new degrees of freedom. And so in the literature, the mostly studied modified gravity theories are basically this tensor theories. Yes?
So I know that there are some theories which have only 2 degrees of freedom, and they are not GR, and they have different solutions, for example, for black holes. Or like there are classical singularities which are not present in these theories, but they still have 2 degrees of freedom.
Yes.
So how would that be a different interpretation?
So this would be, could be a UV modification based on a different geometrical setup, but in the infrared it always gives rise to the GR, right? Like if you think about the Born-Infeld inspired theories, where you also, because you don't have the connection as being dynamical, at high UV it's going to give you some new physics, but in the scales where we basically have general relativity, it will behave like general relativity. Yes. What I am saying is not about the very high UV physics where you might modify it. Yes, very good question. So maybe let me quickly introduce this different modified gravity theories that people have considered. As I said, these tensor theories where massive gravity and bigravity received quite some attention. And so you have basically an additional tensor field in your gravity sector, as the name already suggests. And then, of course, instead of a tensor, you could also have a scalar. These von Neumann interactions can be considered. Or instead of a scalar, you can also have vector tensor theories, like the generalized Procka interactions. So in all of this, you always add an additional tensor, scalar, or vector degree of freedom that propagates in your gravity sector. Okay? And maybe just a warning on the way. So when I say let's modify gravity, we shouldn't get too excited and exaggerate it. Okay? So we always have to make sure that all this tensor, vector tensor, scalar tensor theories whatsoever, they do recover general relativity on small scales. Okay? So we need to find some mechanisms to screen these additional degrees of freedoms on small scales. And I think tomorrow you will discuss different screening mechanism in this different type of theories in order to achieve that, okay? Where you really guarantee that your cat doesn't start flying around, okay? So you really recover general relativity on small scales. Let me start with the scalar field. It's the simplest field that we can work with. And then introduce the scalar field in the gravity sector. Okay, so why should we care about scalar fields? Well, we know they arise in nature, so the Higgs boson. For cosmology, maybe a nice property is they don't break isotropy. This is also very nice. And so again, I can now say what is my fundamental scalar representation of the Lorentz group, and I can write down my Lagrangian. And the simplest is just with the kinetic term and the potential that I can write down for my scalar field is pi. Okay? And so because it's just a scalar field, as you have learned the other day, there is no redundancy in the description of the Lorentz representation for everything which is spin 1, spin 2, higher than spin 0. We will see that there are some redundancies due to the gauge symmetry that you have to have if you want to have an explicit Lorentz symmetry in your theory. So if I add here a mass term, it doesn't make any difference, so it doesn't break any associated gauge symmetry, so I can only just simply write a mass term or a potential term. We will see that for massive gravity, this is going to be a very different property, and we have to be very, very careful. But what about derivative self-interactions? As I told you, okay, with the mass term, potential term, I can add. There's no gauge symmetry, I don't need to be careful. But how about, can I add like derivative higher order interactions here in my Lagrangian and construct more general Lagrangians that would satisfy still the requirement that I want to have second order equations of motion. Okay, and the answer is yes, you can do that. So I impose second order equations of motion, Lorentz invariance, locality, etc. Let me start with the flat space-time where I construct my scalar field. And in this paper, these self-interactions, derivative self-interactions of the scalar field were constructed. They are known as Galilean interactions. They are written here. And so in some of the tutorials, you have seen them already. This type of tuning of the interactions. But let us look at them just a little bit in detail. You see this big pi menu with second derivatives applied on the scalar field appears here all the time. So you have second derivatives and then some traces. So these brackets are some traces of these derivatives. And at each order, you have to tune the interactions in this very specific way. They cannot be any different in order to guarantee that you have really second order equations of motion. Okay? Yes?
What is the motivation to have this kind of Galilean symmetry?
Yeah, there is not really... there was a historical motivation because this type of Galilean interactions were arising as the low energy Lagrangian or physics from a higher dimensional setup, like the DGP model. And there, because it comes from this higher dimensional setup, the Galilean symmetry is just a reminiscent of the higher dimensional symmetry. So it's just a historical reason, but you could give up on the, you can give up on the symmetry. We will see.
Has the ultraviolet completion of that theory been formulated?
UV complete, so these theories of course are non-renormalizable. So you have to use them as we use general relativity as an effective field theory valid up to a given scale. Okay? So there is not a simple Wilsonian way of UV completing this theory. These are non-renormalizable theories.
Which is the advantage of this theory with respect to the scalar tensor and the vector tensor theories? Because you mentioned the three types of theory for modifying gravity. What is the difference between this theory and which theory give better prediction?
Yes, so yes, that's also a very good question concerning their, let's say, quantum behavior of these effective theories. If you just have these Galilean interactions and you imagine you compute some one loop interaction, one loop contour terms, one loop Feynman diagrams or two loops, any loops, then due to the fact how these interactions are constructed and their symmetries, the interactions that you construct are always higher in derivatives, giving rise to not second order equations of motion. So they are kind of separated from this, let's say, consistently behaving Lagrangians. So in this sense, these classical Lagrangians are completely safe from quantum corrections due to the symmetries like the Galilean symmetry, etc. Okay? In the case of massive gravity, I will mention it. It has also very nice behavior for the one loop at least quantum corrections. It's also completely safe from quantum corrections. So this effective field theory that you construct don't receive large quantum corrections on the scale where you are using your classical theory. Okay, but I will mention that when the time comes. Yes, so this guy, when you want, they come in at a given scale where these interactions become basically important. So they have a strong coupling scale, and so once you hit that scale, you cannot use your theory as an effective field theory to describe anything because. So it could be that the cutoff is maybe a little bit higher, whatsoever, but because you are breaking your perturbative unitarity, you can't say anything. But they come in with a strong coupling scale in there, because these are higher order derivative interactions. Okay? But you can imagine it as So you have a scale, let's say call it lambda 3. This scale, all these Galilean interactions living there, they're completely consistent as an effective theory. Beyond that, they might have some sort of a UV complete theory, but not Allen-Wilsonian, some different, something that we don't know. They might have a UV complete theory or not, but we can use them as an effective field theory valid up to a given scale. This lambda 3 scale.
And this lambda 3 much larger than the TVs? Grand unification scale, around that scale, or is much larger?
Yeah, well, this depends on what you want to do with these fields. If you want to use them later on for, let's say, if you try to look at them on solar scales, and this already gives a given constraint on the involved scales in your theory. So if you take naively, this cutoff scale might be around 1,000 kilometers or a few millimeters. So it depends on what you want to do with that. Okay. So I can also write this scalar fields. Maybe just to mention that this scalar Lagrangian, they stop at L5. You cannot construct more interactions in 4 dimension. So the series stops here. In the same way as our low-lock invariance for spin 2 stopped at the level of the Gauss-Bonnet term. And the same thing happens here, so the series stops here. And you can also write them in terms of these Levi-Civita tensors. Remember, this big pi mu was some second derivative, and because this guy is symmetric, there is only one way of how I can contract the indices with the 2 Levi-Civita tensors, by contracting the first with the first and the second with the second Levi-Civita tensor. And so I go next order and I contract the indices in this very unique way, etc. Okay? So I can also write the Galilean interactions just in terms of the Levi-Civita tensors. And actually, using this Levi-Civita tensor, you can understand the stability of quantum corrections better due to the antisymmetry of the Levi-Civita tensor. And this is basically the reason beyond the non-normalizable theorem of these interactions. Okay, but can we generalize these interactions that we just constructed on flat spacetime? Can we generalize them to curved spacetime? Okay? So can we now construct theories, so-called scalar tensor theories? Now I add this additional scalar degree of freedom, let's say this Galilean field that I just considered, into the gravity sector. And if I do that, how can this metric and the scalar field couple in a consistent way? Okay, this is a theoretically interesting question that you can ask yourself, which actually Hornbensky already did. You see, in 1974 already, so quite some time ago. He was a mathematician, and so he constructed just different model by saying, okay, now I have a different gravity model with different ingredients. What is the most general Lagrangian that I can write down with second order equations of motion? And this is what he did. And these are the Hornbensky interactions, these scalar tensor interactions. And they basically were rediscovered by this group here in 2009. And when we look at them, they are basically the same. So you recognize the parts of the derivative self-interaction of the scalar field here that we saw before on flat space-time. But now they are promoted to curved space-time by having the covariant derivative here. But also in L4 and L5, we need to introduce these non-minimal couplings. Remember, to the either low-lock invariance or to some divergenceless tensors, in order to maintain that you have second-order equations of motion. Okay? So you need non-minimal couplings to the gravity sector in order to maintain second-order equations of motion. This is what Hornbensky managed to do in 1974. As I said, he was a mathematician, and he actually quitted mathematics, and you can understand when you see the citation of his paper. This is the times of cited of this paper, and you see in 2010 it basically jumped and received quite some attention due to this paper here, because people started using this scalar tensor theories for cosmology, etc. And people also started constructing theories that go beyond Horndenski, so beyond second order equations of motion. So if you allow to have higher order equations of motion, but you still only have one scalar propagating degree of freedom. And so these are these beyond Horndenski interactions. And you see in 2016, he then suddenly started also publishing himself, even though he quitted mathematics. And here in his acknowledgements, he says, well, so long as I am alive, no one goes beyond Horndenski without me. And then explain the inception of this paper. So he himself also started constructing this beyond Horndenski interaction. Okay, so these are these scalar tensor interactions. Let us do the same exercise now with tensor-tensor interactions, tensor-tensor theories. And I want to introduce an additional F min an additional tensor in the gravity sector. And I brought here massive gravity. So massive gravity immediately tells you that you should have tensor-tensor theories, okay? If you want to be able to write down a mass term for graviton, you cannot avoid the fact that you need a second tensor. Why do you need a second tensor? Imagine you have the Einstein-Hilbert term, and you try to add a mass term, and you try to contract the indices, okay? The indices of the metric with itself, okay? And then you realize you are just writing here numbers, okay? So you just wrote here a cosmological constant. So you cannot contract the metric with itself. You need a reference metric on top of which now the massive graviton can propagate, okay? And this is the reason why you need to introduce this the fiducial metric, this F min u, in your theory in order to be able to write down some mass terms or some maybe other interactions. And then you can ask again the same question. How can then this G and F couple in a consistent way? Okay? And actually this was a challenging task, and it took 40 years in order to write down the consistent theory for massive gravity. And so it was realized by Claudio Devan, Giorgio Gabarazzi, and Andrea Colli in that paper here, a masterpiece, where they wrote the corresponding interactions between the G and F, okay? And it has to have this square root structure, okay? And so if you keep this square root structure between the interactions of the G and F metric, then you guarantee that you don't have any ghost degrees of freedom, as has been shown here, for example, in this paper. And so you can write down all the general interactions as elementary polynomials of this square root of G minus 1F. Okay? And in this way, you can construct consistent tensor-tensor theories. Okay, and how about, yes?
The field has no dynamics.
So F is, for in massive gravity, just a fiducial metric that doesn't have any dynamics. But there's also the bi-gravity version, where you can also make the F dynamical.
You have two Ricci tensor, two...
Yeah, exactly. You have two Ricci Einstein-Hilbert terms, and you can make both dynamical.
Okay.
But so independently of who is dynamical or who not, you have this consistent question about how you couple now the matter fields. So how do you couple the matter fields in a consistent way to G and F? And so there are basically two ways. One is just you couple the F to one type of species and G to another type of species. This way, your Lagrangian that you write down is completely classically stable, but not only that, it's also stable under quantum corrections. Okay, so this theory, mass of gravity, with this type of matter coupling would be stable under quantum corrections as a consistent effective field theory. You could also, if you insist to couple the matter fields to both metrics, you could couple them to this effective metric constructed out of G and F in this very specific way. And if you use now this effective metric, you can couple G and F to the same type of species if you insist on not violating the equivalence principle, etc. Okay? Okay, so now I want to introduce the vector field in the gravity sector. So I can start with the massless vector field, and now I write the massless spin 1 representation of the Lorentz group. It has to come with this gauge symmetry, inevitably. And so I can write the Lagrangian of the Maxwell Lagrangian that is consistent. And this F mu is just the first derivative applied on the vector field. Okay? So now I can ask the same question, and here I have to be more careful than I was doing in the scalar case. Because now in the spin 1, because I have this redundancy, this gauge symmetry, if I now add here any arbitrary interactions, they might either break my gauge symmetry or introduce some additional Gauss degrees of freedom, etc. So I have to be more careful. And so we can again ask the question, can I construct derivative self-interactions for a massless vector field here that goes beyond F mu? And there is a no-go result for that if your vector field is massless. So you cannot construct this type of non-minimal, this type of self-derivative interactions of the massless vector field. But you can still couple it in a non-minimal way to the gravity sector using this double dual Riemann tensor. Remember, I had introduced that as one of the additional divergenceless tensor in 4 dimension. And actually, you see again, Horndansky himself did couple this massless vector field in this non-minimal way to gravity. Okay? But now if you want to introduce a massive vector field, so you are explicitly breaking the gauge symmetry by adding a mass term, then you can indeed construct derivative self-interactions for this massive vector field, and they give rise to a generalization of this of the standard Procca action. So voila, here are the interactions. We don't have to go through them, but in the same way as we did with the scalar, we can construct order by order these self-interactions of the vector field. Okay? In the same way, we can promote them to curved space-time by saying now I want to construct vector tensor theories. So this A mu, how does it couple with G mu in a consistent way? And voila, we can do exactly the same thing as Horndansky did with the scalar tensor theories. So then I can write down the consistent corresponding theories. And you again see they have basically these parts that comes from the flat case. You just put them in the covariant version. But then again, you have these non-minimal couplings. Here also the non-minimal coupling to the double dual Riemann tensor. And this Y is just the mass term, A mu. Okay? And so
it's closed.
sorry?
You only have up to 6 or?
Yes, everything that, because I am in 4 dimension, it stops there. Everything that I would try to construct, again, gives me identically 0. Okay, I can do also some cosmology with vector fields. If I take just the temporal component of the vector field, it gives rise to homogeneous anisotropic solutions. Or if I want to use the spatial components, then I need to have 3 orthogonal vector fields in this configuration. And in this way, with these 3 vectors, I can also construct homogeneous anisotropic solutions that I need for flat Friedmann-Lemaitre-Robertson-Walker solutions. Okay, so I can also do some cosmology with that. How am I doing with time?
1 minute?
Oh.
2. Say 2.
Okay, maybe let me skip a bit the cosmology. in this, maybe let me just also say this, I can also of course construct scalar vector tensor theories where I can unify this Hornbensky scalar theories and generalized Proca vector theories into scalar vector theories, and construct in this way yet another more general theories for gravity. If you want, you could take another 10 vectors, 100 scalars, 10 tensors. So you can do that, and maybe the simplest question where you say I have gravity and I am just adding one additional degree of freedom, and once you know how they look like, then constructing a multiplet of it is just repeating the same interactions. In the same way, if I write massive gravity, but I say maybe I have 3 matrix or 4 matrix, it doesn't matter, it's going to use exactly the same fundamental theory that you have constructed when you wrote down the theory of massive gravity, right? So maybe there is no much gain of doing the same with many multiplets. Okay, and so once you construct these different modified gravity theories, of course they will have different cosmological and astrophysical implications, and it's going to be the task of the next generation, or also the ongoing generation of surveys, satellites that we have. And so we will then be able to use all these cosmological observations, starting with geometrical probes like supernovae or the CMB and BAO priors, or we can use the structure formation probes that we can use, for example, the integrated Salzburg effect, lensing, everything from the way how galaxies cluster. Together now with the astrophysical probes coming from gravitational waves, we can then rule out quite a significant class of these modified gravity theories that are there, and they are theoretically consistent, but whether they have to do something with nature, we can then say that after comparing with observations. Okay? So, yeah, for instance, just to give an example, the recent observation of the 2 neutron stars puts very tight constraint on the propagation speed of the tensor modes, and which is basically equal to the speed of light up to 10 to minus 15. So this is a very tight constraint. And now if you have a modified gravity theory that gives rise to a different speed of tensor modes, you then immediately not, let's say, rule them out, but disfavor them, because they would need to undergo really high fine-tuning in order to be in agreement with observations. Okay? So you see, just with one observations, we can rule out quite a few classes of these observations. If we go back to, for example, the scalar tensor theories here, the observation of the gravitational waves, and I think you have seen it in one of the tutorials. The Hornbensky, this part here, the G5, and then this G4x part modifies the speed of tensor modes, and so you would completely get rid of this type of interactions, and you would remain just with the other ones that is consistent with the tensor modes. So I stop here, thank you very much, and then I take some questions.
To see there.
So in this theory you were mentioning now, if you throw these terms which are not consistent out, would quantum corrections generate them?
Would quantum corrections, yes. I mean, so depending on the theories that you are looking at, for example, in the Hornbensky theories, imagine you are forgetting about this pi dependence, and imagine your theory has a given shift symmetry or Galilean symmetry whatsoever, then it has been shown that due to the symmetry, when you go to the curved spacetime, the breaking will be very weak, or you will have the weak symmetry breaking of this shift symmetry, and it's going to protect you from quantum corrections. But so I guess I would go the other way around than you did. I would start with my Lagrangian and say I'm only considering the subclass of these Lagrangians that are theoretically consistent in the sense that the quantum corrections are not large, right? So I put my theoretical constraints, and among them I then apply the observations like the gravitational waves and other. So concerning the quantum corrections, at least we know that for some subclasses the quantum corrections seem to be under control.
Yeah, I was the one who, like, if you have all these terms, it is clear to me that they are under control. But if you throw some terms out, they may arise.
Yes.
Quantum correction. So are there theories in which they do not arise, or the effect is really small?
Yes, as I said.
Even if you throw them out from scratch.
Yes. Even if they arise from quantum corrections, and if this Lagrangian that I am considering is a consistent thing, then everything that I should obtain should be then suppressed, right? So if I compute all the Feynman diagrams, where the graviton is also now running in the loop, they should come with a scale that is suppressed compared to the Lagrangian that I wrote down, this subclass of Lagrangian, unless I might have done wrong, and this was not my consistent classical Lagrangian to start with.
In the case of the vector tensor theories, you couple the vector to the multiple of gravity, and what's the difference between coupling that case and, for example, electromagnetic with gravitational fields? What do you have to take in account?
Yeah, so if I have electromagnetism, just a photon, the massless spin one field, then the way in general relativity or in the standard model of physics, we couple it we couple it just minimally to the gravity sector, just the square root of minus g in front of the kinetic term of the f mu squared, and etc. So, but if you want to now, if you are willing to modify that one and you say I want to couple it non-minimally to gravity, then we have seen in the massless case there is only one way to do that via this double dual Riemann tensor, and this coupling will come in with its given scale, right? And now I will constrain this tightly if I insist this guy to be the photon, because the observations will tell me that actually the photon doesn't like to couple it coupled in this way non-minimally.
This violates parity, for example, right?
If I can also introduce parity violating terms like f tilde. This one does not, but I can also introduce parity violating terms, definitely.
But this doesn't violate any symmetry.
No. It gives rise to second order equations of motion. It has the massless spin 1 field here, but it just couples non-minimally. And now if you give up the masslessness of the vector field, you can then construct all this generalized Proca interactions. You see now you don't have just this one unique term so nicely, but you have all this bunch of other interactions.
And this does also not violate the equivalence principle, for example. This kind of terms.
Well, I mean, so if you say all the matter fields couple in the same way to gravity, but there is this one massive vector field that couples in this very specific way to gravity, in this sense you are violating it, and you have to make sure that the effects of this guy on solar system is screened, right? Otherwise you would have problems.
Yeah. Okay. I understand the question. How is all this modified theories going with inflation, for example? Are there any ones that can maybe have the observation that C and B?
Yeah, so if you want to use massive gravity, for example, for inflation, you need to use this dynamical version where G and F are both dynamical. Okay. So you can use that, you can construct cosmological solutions for inflation. The problem usually comes when you look at perturbations and they blow up on your face, so they are unstable. But if you couple it, let's say, some of the dark sector to the G effective, then the perturbations behave stable. So this effective metric. In the case of the Hornetsky scalar tensor theories, you can construct inflationary epochs, scenarios. People have even considered scenarios which go beyond inflation, some bouncing solutions or something like that.
But you should take care of the terms that you say that would be ruled out by gravitational waves.
Yes, I mean if I take these terms to be important at high energies and I want to apply that for inflation, they are not probably going to work for dark energy later on.
Okay.
I probably need to select one application.
Okay.
No.
No? Okay, I think we can thank Lavinia again. And,